Hello and welcome to this look at some practice questions looking through how to deduce a weak acid's strength from its pKa values and constructing relevant conjugate acid-base pairs from this. So let's first look at how pKa value relates to the strength of an acid. This is our first question. It wants you to put the following three acids in order of their strength from the weakest to the strongest, but all it gives you is the pKa value. So we have to go back to the Ka value and from that really go back to what acid strength really means. So as you probably know already, an acid's strength is related to the number of hydrogen ions it can release on dissociation in moles per decimeter cubed. So a stronger acid will dissociate more hydrogen ions than weaker ones, so the hydrogen ion concentration is always a good measure of the strength of an acid. In a weak acid, what we do is we create something called a Ka expression. It's a little bit like a Kc expression in equilibria. So the products, i.e. the dissociated hydrogen ions and the conjugate base that's left behind, are put on the numerator, and the denominator carries the concentration term for the undissociated weak acid. So if we concentrate on the H plus concentration term, if that increases, then obviously that weak acid is getting stronger for a weak acid, isn't it? So you would expect also that at the same time the concentration of A minus will go up because they're released at the same time as each other. This would mean that the numerator in the expression increases. So therefore the relationship between Ka and hydrogen ion concentration is linear. As one goes up, so does the other. However, if we take the pKa value that we're given, the relationship between Ka and pKa is logarithmic. So pKa is minus log of Ka. What this will mean is that as Ka goes up, pKa will decrease. So from this we can conclude that the stronger the acid, the higher its dissociated hydrogen ion concentration and the lower its pH value. Also, the greater its Ka value and the lower its pKa value. So looking at the acids, the acid with the lowest pKa value is going to be the strongest. So that's chloroethanoic acid. The acid with the highest pKa value is going to be the weakest, so that's ethanoic acid. And benzoic acid sits in the middle. So the question wants the acids in order of their strength from the weakest, so the weakest being ethanoic, to the strongest being chloroethanoic, with benzoic acid in between them. The next part of the question wants us to use this conclusion we've come to construct conjugate acid-base pairings. So putting our conclusion at the top, our answer, what I've done is I've highlighted the strongest acid in each of the two acids in part A, B, and C. So for example, out of chloroethanoic acid and benzoic acid, chloroethanoic acid's pK value is 2.9 and benzoic acid's pK value is 4.2. So chloroethanoic acid is the stronger of the two. So that's why I've highlighted it in pink. I've done the same down here and here. So this is the acid which will behave as an acid. Even though they're both acids, this will actually behave as a quote-unquote acid more effectively. This will mean that the weaker of the two acids must behave as a base. So what happens when we put an equation together? How do we decide what the conjugate acid-base pairs are? Well, if we go back to our stronger acid, this acid is assigned as acid 1, or you can just put A1 underneath it. That's where they've got two lines, so they'll put your A1 and your B1, etc. down here. Going to the weaker acid in each pairing, so with benzoic acid, for example, this is a base, so it's assigned base 2 or B2. So we write them in like that. So what we now have to do is look and see what happens to A1, to acid 1. It turns into this species, so this species must be base 1. This species, by the exchange of a proton, turns into this species. So those two must be an acid-base conjugate pair as well. So we put B1 and A2 accordingly on the right-hand side. So if you're watching this, why not pause it and have a go at the other two using the same idea? And I'll come back to you in a minute. Okay, welcome back. I'm assuming you've had a pop at those two. So let's have a look at part B now. Okay, so let's look at the pairing in part B. So you've got benzoic acid, which has a pKa value of 4.2, and ethanoic acid, which has a pKa value of 4.8. So if you put those into an equation, what you always do is whichever is the acid will lose a proton. So we've decided that based on the pKa value of 4.2, that benzoic acid is the stronger of the two. So that's paired up with this species over here. We've taken a hydrogen away from it. With ethanoic acid, which has a pKa value of 4.8, that's the weaker of the two acids, that gains a proton, so that becomes CH3COOH2+. And we can pair them up like this. So similarly, you can do the same thing using the same ideas for the third one. Okay, hopefully this has been useful. As always, thanks for listening. Until next time, see you soon.